Alright, in this video we are going to look at linear differential equation. Definition. A first order differential equation is called linear if it is of the form dy by dx plus px times y equal to qx. So this is the standard form of linear differential equation. Well, note that this function p and this function q, they are just functions of x. So you cannot have y in p and q. Alright, once you have linear differential equation, then, well, let's try to look at the idea behind the solution. So I can simplify this thing and it will be dy by dx equal to qx minus px times y. And then after that, I can multiply both sides on by dx. So I get dy equal to qx minus px times y. Everything multiply dx here. And then I move everything to the left hand side. So I have px times y minus qx. This thing in parentheses multiply dx plus 1 dy equal to 0. So this is now in the form m dx plus n dy equal to 0. So I let mxy to be px times y minus qx, and I let nxy to be 1. So the idea is I'm going to check if this differential equation is exact, and then after that I compute partial derivative of m with respect to y. Because p and q are functions of x, so differentiate px times y, so I get px, and differentiate qx, I get 0. So my m sub y is just px, and then I differentiate n with respect to x, so this is completely 0 because 1 is just a constant. And then so now this differential equation is not exact, right? Because m sub y is not equal to n sub x. However, if you compute m sub y minus n sub x and then multiply by 1 over n, so you're gonna get px minus 0 and then multiply by 1 over 1. So compute this thing and then it goes back to px. So now you can see that this is just a function of x. Well, from the thing that we learned from the previous topic, if we have a situation like this, so we say that the integrating factor is mu equal to e to the integrate px dx, right? This is from the previous topic. And once we have the integrating factor, we can multiply the original equation with the integrating factor, and then after that the equation will turn to exact differential equation. Well, but before we do that, so let's compute d mu. So this thing gonna be handy later. So d mu is equal to d times e to the integrate px dx, and that is e to the integrate px dx d integrate px dx, right? Because this is by the chain rule. When you have differentiate of e to the u, so you get e to the u du, right? And then after that you have e to the integrate px dx, right? And differential operator and integrating operator, they cancel each other, so you have px dx left. And then because e to the integrate px dx is just mu, So this thing is going to be mu times px dx. So we're going to use this thing later. Now we come back to the original differential equation, pxy minus qx dx plus 1 dy equal to 0. Once you multiply an integrating factor mu, so you have mu px y dx minus mu qx dx and then plus mu dy equal to 0. This thing we multiply by an integrating factor mu, and then after that I'm going to move mu qx dx to the right hand side. So I have mu px y dx plus mu dy equal to mu qx dx. And then after that, from the previous slide, we know that, well, mu px dx, this thing, I'm gonna copy this thing and paste it here. So this thing we know that it is equal to d mu, right? This is from the previous slide. So we're gonna group mu px dx together. So we have mu here, px here, and dx here. We're gonna group them together and then call it d mu. So this thing gonna be y d mu plus mu dy equal to mu times qx dx. And on the left hand side, this is the formula for total derivative of mu y, right? So this thing gonna have d mu y, because the d mu y is going to be mu dy plus y d mu anyway, and that thing is equal to mu times qx dx. And then from here you can solve for the total derivative equation. So you're gonna get mu y equal to integrate mu qx dx plus c. And once you move mu to the right hand side, so you get y equal to 1 over mu times integrate mu qx dx plus c. So this is a general solution of linear differential equation. So this is a general solution. So when you do a problem, you can just use a formula here. You don't have to prove it again. Well, the formula now is ready to use. So once you figure out what is your P, what is your Q, then you are ready to plug in formula, and that's all for linear differential equation. Well, let's do some examples. Example 13, find the general solution of y prime minus y minus x e to the x equal to 0. So first I'm going to simplify this thing. So I am going to start by change y prime to dy by dx. So this thing is dy by dx minus y minus x e to the x equal to 0. So note that the standard form of linear differential equation is dy by dx plus px times y equal to qx. So first we have to figure out what is our p and what is our q. So I'm going to simplify a little bit. So I have dy by dx plus negative 1 times y equal to x times e to the negative x. Now you can see clearly that our p is negative 1 and our q is x e to the x, right? So I'm gonna let my px to be negative 1 and qx to be x e to the x. Alright, so now I have p and q. Once I have p and q, so I already know that the solution is of the form y equal to 1 over mu integrate mu q dx plus c. But first of all, I'm going to find an integrating factor. So the integrating factor is mu equal to e to the integrate px dx. So this is e to the integrate -1 dx. So this is just e to the -x. That's it. That is our mu. So now the general solution is, well, we already have the formula. So let me share this thing. Alright, is the formula is y equal to 1 over mu times integrate mu qx dx plus c. Alright, then that is y equal to 1 over e to the -x, and then integrate e to the -x times x e to the x dx plus c. So I just replace mu by e to the -x, replace mu by e to the -x, and replace qx by x e to the x. And after that I simplify this thing. So this is y equal to e to the x. Well, you can see that e to the -x and e to the x, they cancel, right? Because once you multiply them together you get 1. And then you have integrate x dx plus c inside the parentheses, and that will give you e to the x times x squared over 2 plus c. Alright, so to sum up, the general solution is y equal to e to the x times x squared over 2 plus c. So you don't have to simplify more. This is already acceptable, right? Super easy. You already had formula, so just plug in, done. Alright, let's do example 14. Find the general solution of xy plus x cubed in parentheses dx minus 1. Well, let's change this thing to plus 1 plus x squared in parentheses dy equal to 0. So note that I changed the question from 1 minus x squared to 1 plus x squared. This is my typo. Alright, so here you have to start by simplifying this differential equation. So we are going to get xy plus x cubed dx equal to 1 plus x squared dy, right? And that is dy by dx is equal to xy plus x cubed over 1 plus x squared. And then now you can separate the right hand side to x over 1 plus x squared times y, and then plus x cubed over 1 plus x squared. Alright, and then after that you simplify a little bit, so just move the term x over 1 plus x squared times y to the left hand side. So you're gonna get dy by dx plus minus 1 minus x over 1 plus x squared times y equal to on the right hand side you can cancel this thing, so 1 plus x squared, and then on the top you have x times 1 plus x squared, right? So you cancel 1 plus x squared, and then on the right hand side you have just x here. Well, this is your linear differential equation now. And then now you can see clearly that your px is going to be this thing, and then your qx is just your x. Now the integrating factor is mu equal to e to the integrate px dx. Well, this is e to the integrate negative x over 1 plus x squared dx. then how do you integrate this thing? So this is let's say e to the negative integrate x over 1 plus x square d1 plus x square over 2x, right? And then you cancel x here. Then after that you get e to the negative 1/2 and then logarithm of absolute 1 plus x square. Well, because 1 plus x square is always positive, so you can ignore absolute value and say this is just parenthesis. And then after that you use the property of logarithm. So this is e to the log 1 plus x square raised to the negative 1/2, and that is just 1 plus x square to the negative 1/2. So this is our integrating factor mu. So the general solution is y equal to 1 over mu times integrate mu qx dx plus c. Then you have y equal to 1 over 1 plus x square raised to the negative 1/2, and then integrate 1 plus x square raised to the negative 1/2 x dx plus c, right? Because qx is x. And then after that you have y equal to let's simplify this thing, so you get 1 plus x square to the 1/2 and then integrate. Alright, this thing is going to be 1 plus x square raised to the negative 1/2 x d 1 plus x square over 2x plus c. And then you can cancel x here. So what you have left is you have y equal to 1 plus x square raised to the 1/2 and then multiply 1/2, and then to integrate this thing, so you have it seems like you want to integrate u to the negative 1/2 du. So this thing is going to be 1 plus x square raised to the 1/2 over 1/2, right? This is by integration technique, and then plus c. And then after that you can see that your constant 1/2 cancel. So at the end you get y equal to 1 plus x square to the 1/2 times 1 plus x square to the 1/2 plus c. Well, this is your general solution. Lastly, we're gonna wrap up this chapter by looking at Bernoulli differential equation. So let's take a look at the form of this differential equation. So a Bernoulli differential equation is a differential equation of the form dy by dx plus px times y equal to qx times y to the n. The difference between Bernoulli and linear differential equations is on the right hand side. So if you have y to the n attached with your q, so this is called Bernoulli differential equation. To solve this thing, you're going to use the idea of linear differential equation. So first, divided an equation by y to the n. So this will give you y to the negative n dy by dx, and then plus px times y to the 1 minus n, and then on the right hand side you have just qx. So we obtain this equation because we just divided everything by y to the n, and then you can see some cancellations. And then now after that we're gonna let c to be y raised to the 1 over n. So this is our new variable c. So the idea is we're gonna change this equation into linear differential equation in terms of c and x. Alright, so once we let c equal to y raised to 1 over n, so if we compute derivative of c with respect to x, well, we have to use a chain rule first. This is going to be dc by dy times dy by dx. This is by the chain rule. And then after that, well, dc by dy is going to be 1 minus n y to the negative n. This is by just differentiate y raised to the 1 minus n. So you get 1 minus n y to the 1 minus n minus 1, which is negative minus n. And then after that, well, multiply this thing by dy by dx, right? And then once you simplify this thing, so you're gonna get that y to the negative n dy by dx, which is this term. This is going to be equal to 1 over 1 minus n dc by dx. So you have this thing with you, this equation that I boxed in red. And then you can see that the left hand side, y to the n dy by dx, this is the same thing with the one that I highlight in green as well. So we're gonna replace the one that I highlight in green by using that equation in the box. So we're gonna have 1 over 1 minus n dc by dx plus px times y to the 1 minus n equal to qx. Alright. Once we get this differential equation, so now you can change y to the 1 minus n to c too. So this is 1 over 1 minus n dc by dx plus px times c equal to qx. And then to make it more clean, I'm gonna multiply by 1 minus n to this equation. Well, this thing will be dc by dx plus 1 minus n px times c, and then equal to 1 minus n times qx. Well, this will be a linear differential equation now. So this is a linear differential equation in terms of c and x, right? And then now you can use the same technique as before to solve this differential equation. Well, let's learn how to do this by examples. So example 15, find the general solution of dy by dx minus 1 over x times y equal to x times y squared. So you can see first that this is close to linear differential equation. The thing that make it harder is going to be on the right hand side, because you don't have just a function of x, you have x times y squared. This thing is called Bernoulli differential equation, because you have a differential equation of the form dy by dx plus px times y equal to qx times y to the n. So you just have y squared attached here. So that means this is now a Bernoulli differential equation. Alright, let's first do this by divided everything by y squared first. So I'm gonna get dy by dx, well, multiply everything by y squared, so I get 1 over y squared here, and then minus 1 over x, y over y squared, so I get 1 over y, and then on the right hand side I get just x. So this is just divided everything by y squared. Well, once you get into the form of this differential equation, so you can let c to be y to the negative 1 or 1 over y. So the idea is you are going to make a substitution. So just let the thing that I highlight in light blue here to be c. Or you can memorize that you're gonna let c to be y raised to the 1 minus n. Well, here n is 2, so that means c equal to y to the negative 1 or 1 over y. And then after that, well, you're gonna compute dc by dx. So then you have dc by dx. By the chain rule, you're gonna get dc by dy times dy by dx, right? And then because c is y to the negative 1 or 1 over y, so dc by dy is going to be negative 1 times y to the negative 2 and then times dy by dx. So simplify a little bit, so this is negative 1 over y squared dy by dx. Well, and then you can see now that 1 over y squared dy by dx, this is negative dc by dx, right? And then once you have negative dc by dx here, you can substitute back into the original equation star here. So we have, well, just replace that thing back into equation star. So you have this negative dc by dx equal to minus 1 over x times c equal to x. So now this is a linear differential equation. In terms of c and x, right? And then now you can use the linear differential equation technique as before, right? So here you're gonna have px equal to, okay, let me simplify more because I need plus sign on the left hand side. So I have dc over dx plus 1 over x equal 1 over x times c equal to negative x. And then here now I have my px equal to 1 over x, and then my qx equal to negative x. Alright, we're gonna solve this thing. So the integrating factor is e to the integrate px dx, which is, well, our px is 1 over x, so it is e to the integrate 1 over x dx, which is now e to the log x, and that is just x. So this is our integrating factor mu. So mu equal to x. And then after that, the general solution is, well, here now you have to use c instead of y because you have a differential equation, a linear differential equation in terms of c and x. So we're gonna use c instead of y. So it's gonna be c equal to 1 over mu times integrate mu qx dx plus c, and this thing is 1 over x integrate x. Our qx here is negative x, and then dx plus c. Alright, and that is 1 over x integrate negative x squared dx plus c, and that is 1 over x minus x cubed over 3, and then plus c. Now remember that on the left hand side you have c. This is not y, so you have to convert c back to y. So from the previous substitution, we let c equal to 1 over y. So actually here c is equal to 1 over y. So that means your final answer is here. The general solution is y equal to 1 over x times negative x cubed over 3 plus c. So this is your final answer. So don't forget to convert c back into y as well, because your original question asks you the general solution in terms of y. Alright, so let's move to example 16. Alright, let's do the last example for this chapter. Solve the initial value problem dy by dx plus y over 2x equal to x over y cubed with the initial condition y1 equal to 2. Alright, let's simplify this thing first. So you're gonna have dy by dx plus 1 over 2x times y equal to x times y to the negative 3. So the reason I simplify to this form because I wanna show you that this is a Bernoulli differential equation, right? Well, you can see that our px is 1 over 2x and then our qx is just x. Well, the thing that is hardest to work with is y to the negative 3 here, right? That's why it's called Bernoulli. So we're gonna convert this differential equation to linear differential equation. First of all, I'm going to divide everything by y to the negative 3. So divided y to the negative 3. That's we're gonna get 1 over y to the negative 3 dy by dx plus 1 over 2x y over y to the negative 3 equal to x. So every time you start doing Bernoulli differential equation, you should start by this step. So divided everything by y to the n. And then after that, well, let me simplify a little bit so it's more clean. So here I'm gonna have y cubed dy by dx plus 1 over 2x times this is y to the 4th power now, and then equal to x. Alright, and then after that we're gonna use a substitution. So we're gonna let c to be this thing, y to the 4th power, right? Because in the theory we say that we're gonna let c to be y to the 1 minus n. This case n is equal to negative 3, so this is c equal to y to the 4th power. So anyway, you can memorize that what are you going to let to be c is going to be the middle term here that I highlight in green. It's always like this. And then next we're gonna find dc by dx. Alright, then dc by dx is going to be dc by dy times dy by dx, and that is differentiate c with respect to y. Alright, so I get 4y cubed and then dy by dx, and you can see now that y cubed dy by dx equal to 1 over 4 1 over 4 dc by dx, right? And then now I can just use this equation in the box to plug in back to this equation that I just point out, and then what I'm gonna get is 1 over 4 dc by dx plus 1 over 2x times y to the 4th power equal to x. dc over dx plus 2 over x y to the 4th power equal to 4x because I multiply by 4. Multiply by 4. And then now I can switch my y to the 4th power to c as well because they are the same thing. Alright, this differential equation, this is linear. This is linear. In terms of c and x. Well, we're gonna solve this thing. Alright, so let's copy this and then alright, paste it here. Alright, we're ready. Now we can see that our px here is going to be 2 over x, and our qx here, this is 4x. So now we have the integrating factor. factor is mu equal to e to the integrate px dx, which is e to the integrate 2 over x dx, which is e to the 2 log absolute x, right? And that is e to the log of x squared, and then that is just x squared. Alright, now we have mu equal to x squared. Now the general solution is c equal to 1 over mu times integrate mu qx dx plus c, and that is 1 over x squared times integrate x squared times 4x dx plus c, and that is 1 over x squared integrate 4x cubed dx plus c, and that is 1 over x squared 4x to the 4th power over 4 plus c. So you have 1 over x squared times x to the 4 plus c here, and then on the left hand side here you have c, which is y to the 4th power. Alright, then if you simplify a little bit, so that means the general solution is x squared times y to the 4th power equal to x to the 4th power plus c. Alright, this is my general solution, but the question asks for particular solution at y1 equal to 2. So when x equal to 1, y equal to 2. So when x equal to 1, y equal to 2. So we have, well, let's substitute this thing. So x equal to 1, y equal to 2, x equal to 1, and then plus c here. So you have 16 equal to 1 plus c. So that c is 15. So the specific solution is x squared times y to the 4th power equal to x to the 4th power plus 15. Alright, that is your final answer for this question. And that's all for this chapter.